Hello, everyone. Welcome. I hope you're all as excited as I am, as today we'll be learning about a new technique for key management. This is the work of Stanisław Jurecki, Hugo Krawczyk, and myself. I'd ask that if you have any questions, please save them to the end, where we'll have some reserved time. So with that, let's begin. We'll start by reviewing the existing approach used by all of the major cloud services. Next, we'll see how with a little cryptography, this could be done in a much better way, where the cloud doesn't see the keys that it manages, where rotation is atomic and nearly instantaneous, and where it can even be engineered to be resilient against hacks. This brings us to our results. We've created a proof of the security for this approach. We've implemented and tested a prototype implementation, and we've achieved favorable performance. Finally, we'll end with conclusions and questions from the audience. So let's see how key management is done today in the cloud. First, we'll define all the components. There's the client, designated by C. This is who wants to have their keys managed. Next, there's this big amorphous cloud. It may contain any number of services, but for our purposes, we're only concerned with two of them: the storage server and the key management server, or KMS. This view is a rough approximation of all the major cloud players: Amazon, Microsoft, IBM, Google, etc. Each has their own storage service and key management service. These clouds also have all adopted what I've referred to as the wrap-unwrap method for key management. You can think of it as an encryption service, but one that's limited to very small messages. And because that size is limited, the client can't use the KMS for bulk data encryption. They can only use it for encrypting key material. So let's see how this works. The client starts with a key used for bulk data encryption that it wants to have protected. We refer to this key as the data encryption key, or the DEC. The client can have as many DECs as they want, perhaps even one per file or per object. To protect the DEC, the client issues what's called a wrap request, where it sends both the client ID and the DEC to the KMS. This link is secured by a TLS, which provides secrecy for the DEC. When the request is received by the KMS, before the KMS processes it, it will authenticate the client. And if it's valid, it will process the DEC and create what's called a wrap. The wrap is the DEC encrypted under a client master key designated by K. K is held by the KMS server on behalf of the client, often in an HSM. Once it's generated, it's not stored by the KMS, it's just returned in the response back to the client. Now that the client has this secured wrap, it's free to store it where it will. For example, it might store the wrap and the object ciphertext to a storage server. Here, the object ID, the wrap, and the ciphertext are all stored together. This is an approach recommended by several cloud providers. Now, to unwrap, the client begins with a wrap already in hand. It may have come from just reading an object from the storage server, for example. Now, to convert this wrap back to the DEC so that it can be used for decryption, the client invokes the unwrap method, sending, again, its ID and now the wrap to the KMS. The KMS authenticates the client, and then we'll use that client's master key to decrypt the wrap and recover the DEC. Once the DEC is recovered, it's again returned to the client, and again over a secure TLS link. And now with the DEC, the client can decrypt bulk ciphertexts that are protected by it. This is a very scalable solution. The master keys of the clients are usually stored in a hardware security module, or HSM, where space is limited. This approach allows the client to maintain an unlimited number of DECs outside of the HSM, while the KMS only has to store one key per client. However, this approach has its shortcomings. So let's consider some of them and see all the ways that this system might fail. So the first thing to recognize is that the security of the DECs relies on TLS. This sounds good in theory, but in practice, TLS is quite fragile. First, it depends on each of the roughly 400 certificate authorities that are trusted by default, all operating flawlessly. Second, it depends on TLS not being prematurely terminated. In large-scale cloud systems, there are often load balancers, firewalls, intrusion detection systems, where TLS might be terminated early before it reaches the KMS. And from the point it's terminated, everything beyond can see those data encryption keys in the clear. Third, for TLS to work as intended requires proper configuration and implementation. Is the client configured to ignore certificate errors? Is it actually doing full X509 certificate validation? Is it downloading CRLs and checking with the OCSP responders, etc.? If any of those steps are skipped, then the client is making itself vulnerable to have its keys exposed. There's also configuration on the cloud. In shared computing environments, you often see the subject alternative name field be exploited, where many server names will be stuffed into a single certificate, and then the private key of that certificate might be shared on many servers and services. Again, this endangers the client keys. These cases might seem unlikely, but in my experience, I've witnessed all these behaviors firsthand in the wild. And if everything isn't done perfectly, it leaves the door open to a potential man in the middle who can protect the security of TLS, who can pierce the protection of TLS. Such a man in the middle can trivially gain access to the data encryption key. And even in normal operations, TLS has to be terminated somewhere. Any insider beyond that point, again, can trivially gain access to the encryption key both during wraps and during unwraps. It's not just malicious actors you have to worry about, but also accidents. How certain are you that your data encryption key won't be accidentally logged to some hard drive? It might seem like an easily avoided problem, but many operating systems, when they crash, or when an application crashes, or when they run low on memory, can write the contents of the memory to disk. And then what happens to that disk when it's thrown in a dumpster sometime later? Another problem specific to this approach impacts data reliability. If either maliciously or accidentally somehow the wrap gets corrupted, this can happen due to random bit flips in memory and so forth. The result for the client is almost certainly irrecoverable data loss, because the client will store a wrap that's been corrupted. It won't be able to unwrap that properly, and then it will never be able to decrypt any data that it's encrypted under that deck. And another thing to note is it's not just during the wrap that the key is vulnerable, but upon every single unwrap, so every time the data is accessed. And again, this leads to another problem where the KMS, you're inadvertently leaking information about your file access patterns. If you have to access the same key every time you decrypt one particular file, well, now the KMS or man in the middle will know every time you access that file. So there must be a better way of doing things, one that can retain this functionality, but addresses these security concerns. And as it happens, there is a way. It preserves the role of a third party who authenticates access to keys, but importantly, it doesn't give that third party access to see those keys. Our improvement uses what's called an Oblivious pseudorandom function, or OPRF. So let's review what an OPRF is and how it works. An OPRF is a lot like a conventional PRF, except it's computed by two parties. One of those parties has access to the input and the output of the function, but not the key. The other party has access to the key, but learns neither the input nor the output. So here we have our two parties, Alice and Bob. The first party, Alice, starts with an input she wants to run through the OPRF. Let's call that input X. Bob starts off with his key, K. Now, Alice can't give X directly to Bob. That would violate the contract of the OPRF. So Alice must first blind it. She chooses a random blinding factor, B, and combines it with X. For example, if X is some group element, she might compute X to the power B to obtain a new group element. And if B is chosen uniformly, this forms a one-time pad encryption of X. Alice thereby has unconditional security for X. The blinded value will reveal no information. Therefore, she can freely send this value to Bob. Now, Bob must combine this key with the blinded value in a way that will allow Alice to reverse her blinding later, and also in a way that doesn't reveal X, or doesn't reveal K to her. So one way for Bob to do this is to simply exponentiate the value using his key K. Assuming Alice can't solve the discrete logarithm, she's prevented from learning the key. So far, so good. Bob returns the result to Alice, and Alice can then raise this result to the reciprocal of B to remove the effective B entirely, leaving Alice with simply X to the K. So the output of the OPRF might be defined, for example, as the hash of X to the K concatenated with X. So let's see how we might use this to build a better key management system. As before, we have a client and a KMS. The KMS performs the same role of authenticating client requests and restricting access to a client-specific master key. And the client will still obtain DECs and wraps through interactions with the KMS, but now we will leverage obliviousness to gain some advantages. The client, like Alice, chooses an arbitrary X value, and it also blinds it with a randomly chosen blinding factor. Now, instead of the usual wrap request, the client will send its ID and the blinded value to the KMS. Again, the KMS will authenticate the client, and if it's authorized, perform an exponentiation on the blinded input using that client's master key to produce what we call a blinded DEC. The KMS returns the blinded DEC as a response. The client removes the blinding factor by raising it to the reciprocal of B and obtains X to the K. The client now computes the OPRF output for X and uses the result as the data encryption key. The X value is now treated similarly to the wrap. The wrap can be unwrapped in the future to recover the DEC simply by repeating this process with the server using the same X. So let's consider what we've gained. If a man in the middle can penetrate TLS, they learn only the client ID, not the DEC. X to the B, again, is a one-time pad encrypted value, so it yields no information to the attacker. What about insiders within the KMS? What do they learn? Here they see only a blinded input and a blinded output. At no time is an unblinded value available inside the KMS, not even within the HSM. The client doesn't need to worry about accidental logging either, since nothing here is private. The same follows for a man in the middle who intercepts the blinded DEC returned by the service. Since the client is the only one that knows the blinding factor, the client's the only one that can recover the key from it. And because both wrapping and unwrapping appear identical over the wire, both cases are protected. So this frees the client from having to worry about bad CAs or where TLS is terminated, whether things might be accidentally logged. The DEC lives only on the client machine and never leaves it. The only thing the client has to trust is the math of the OPRF. So if you've had your coffee, you might now be wondering, what if during the return trip, the man in the middle corrupts the blinded DEC? Won't this lead to irrecoverable data loss, just as before? That's a great question, which leads to the next slide. So in the original KMS, the master key is a symmetric key performing a symmetric encryption. Therefore, a client who doesn't know the wrap can't, or who doesn't know the key K can't verify the wrap. However, in the OPRF, the application of K is an asymmetric operation. Since K is behaving like a private key, that means there is some corresponding public key. Knowledge of this public key is sufficient for clients to efficiently verify both the proper computation and the absence of corruption for the value returned by the KMS. So here are some examples of how that can be done. It's possible whether you use RSA keys, pairing-based cryptography, or even vanilla Diffie-Hellman or elliptic curves. So key verifiability, therefore, protects the client from irrecoverable data loss resulting from either accidental or malicious corruption of the wrap value. So if we now assume that there's this public key, and if we assume the client knows the public key, we can in fact do even better. So here, let's say the public key is G to the X, and let's call that public key Y. The first benefit now is that the client can generate both the DEC and the wrap non-interactively, that is, without even having to talk to the key management server. To do this, the client generates a unique random value R, and the DEC is defined as the hash of Y to the R. The wrap is then defined as G to the R. So this allows the client to perform encryption of new objects without even bothering to contact the KMS. It's only during unwrapping you need to talk to the KMS. So because this can be done offline, a second advantage is it allows a type of public encryption where other users could encrypt data to the client while not being authorized to decrypt it. So this supports some new use cases such as secure file sharing. Only users who are authorized to unwrap using that client's key can decrypt. So let's see how unwrapping works. The client starts with a wrap W. The client again blinds it with B, sends it to the KMS, and again, the KMS will exponentiate it if the client's authorized. This goes back to the client, gets unblinded, and now the client has W to the power K. Now for the client to get the DEC, all it has to do is hash W to the K. And the reason that it gets the same DEC is that W, if you recall from the above definition, is G to the R. So what we've computed is G to the R to the K, which of course equals G to the K to the R. And G to the K was Y, so we've really, W to the K is the same as Y to the R. We've recovered the same key. So this can vastly reduce load on the KMS if you have a write-heavy or encryption-heavy workload, such as in archival use cases. And there's still other advantages. So anytime a key is exposed, revoked, or expired, you want to stop using that key as soon as possible. Time is of the essence to limit what the attacker might access. So in the cloud, a single client master key might protect millions of files. And rotation is generally speaking, is a laborious and time-consuming process. The client has to obtain each of the wrapped values, send them to the KMS to be unwrapped with the old key, rewrap them with the new key, and then store that updated wrap again. And it has to repeat that process potentially millions of times, so it could take months. Fortunately, it's possible to do better. This new model enables nearly instantaneous rotation to a new key, thereby restoring security for the client's data. So let's see how this works. The client starts by issuing a rotation request to the KMS. Upon reception and authentication of the request, the KMS performs three functions. First, it generates a new key. We'll call that key K prime. It then computes a delta, which is K divided by K prime. It sends this delta to the storage server. And then finally, it deletes K. That's it. The KMS can now tell the client that the key has been rotated. The old key has been destroyed and is no longer of use to any attacker who might have it. In the background, and upon every read request, the storage server is updating each of the wrap values using this delta. So let's consider what's held by the storage server. It's effectively a set of triples of the object ID, the wrap, and the ciphertext. So when the storage server receives the delta, it begins updating the wraps by exponentiating them with the delta, like so. So you see it's updating each of the wraps just by raising it to the power of delta. So if the client issues a read to the storage server that hasn't been updated, the storage server has to, on the fly, update the wrap before it returns it to the client. Now the reason this all works is because the updated wrap value, let's call that W prime, when raised to the power of K prime, equals the old wrap to the power of the old key. This follows due to how W prime is defined as W to the power of delta, which is W to the K divided by K prime. So when you look at this equation, you can see the K primes cancel out and you're left with the original encryption key. However, importantly, the old key can't be used to decrypt this updated wrap value. Importantly, security or privacy is also retained by the client because at no time does the storage server ever see the original deck, therefore it can't leak ciphertext. It can also be done in parallel if you have dozens or hundreds of storage servers. They can all work on behalf of the client. So because everything's done on the fly during reads, rotation appears instantaneous from a client perspective, and attackers are immediately cut off from exploiting any keys they might have in their possession. So a final benefit I want to mention is threshold security. In a conventional KMS, anytime there's a breach or a data loss by the KMS, that catastrophically impacts the client. The updatable Oblivious KMS, however, supports threshold security, meaning we can now tolerate both destruction and exposure events. So here's an example depiction of that. We have, again, the client, but now note there are 3 KMS servers. There's also this new guy in the middle called the proxy. The proxy, in fact, can live anywhere. It can exist as logic in the client, as functionality within the KMS, or as its own independent node. So let's see how everything works. As before, the client sends its blinded value to the proxy. Now the proxy will multiplex that request to each of the KMS servers. Now, not all of the servers have to be available. For example, KMS2 might be entirely infiltrated, or it might be crashed and unresponsive. This doesn't matter so long as we can contact at least a threshold number of servers. So in this example, it's a 2 out of 3 system. So long as we can talk to any 2 of the servers, we can get a result back. And the other thing to note is none of these servers actually hold the original K. Server 1 holds K1, server 3 holds K3, and this is why we can tolerate breaches. So the attacker might have access to K2, but K2 alone isn't sufficient to unwrap client keys. So once these online servers respond with their results, the proxy interpolates them to create a single combined aggregated result, which actually solves to the same blinded wrap to the power K that the client would have received if it interacted with a single server that held K. So this goes back to the client, and then everything else is the same, and the client might be completely ignorant of the fact that there's this whole threshold deployment behind the scenes. So what's nice about this is you could start on day 1 with a single server deployment, and then transparently to clients upgrade it to a threshold deployment in the back end. So this is all based on just generic secret sharing, and it uses interpolation in the exponent. So as this slide shows, we've uncovered about a dozen benefits of the updatable Oblivious KMS. Now as for results, this seems great on paper, but is the system practical? So of course, a new protocol shouldn't be used if there's no proof it's secure. Fortunately, our paper includes a proof. The attacker basically is restricted to the very minimum amount of information possible. As far as performance, this shows that so these performance numbers reflect a single CPU core, and we see that all the operations by the client, the proxy layer, the servers, the storage servers, can operate at thousands to tens of thousands of operations per second for a single core. So with these numbers, a single storage server can update 1 million wraps in 68 seconds of CPU time of a single core. In addition to these micro benchmarks, we created an end-to-end prototype between some EC2 machines, and we achieved over 30,000 unwrap operations per second between the client and server over HTTPS connections. A best practice is to keep keys, especially master keys, within HSMs. So all of this work, designing a new key management system, wouldn't be very useful if we couldn't use existing HSM infrastructure and conform to existing policies. Fortunately, most HSMs already support this new form of key management. And this is because nearly all HSMs are PKCS11 standard, which defines a method called ECDH1 derive. This is the method that does the exponentiation on an elliptic curve. So in the 3 implementations we tested, we found all 3 HSMs supported this method. And every HSM that supports this method can be used to build a KMS like the one we described that's oblivious, updatable, verifiable, and has threshold security. And we actually created an implementation against 2 of these HSMs, and everything worked. So as for performance, that's always the big elephant in the room. And to our surprise, we found that a major HSM manufacturer, which is used by most of the clouds, their product sheets actually say that they can perform more ECC operations per second than ASGCM operations per second. We believe this is because they use hardware acceleration internally. So in summary, this approach offers better security, it offers good performance, it's minimally disruptive, and in short, we believe all clouds should be doing it this way. So with that, we have a few minutes for questions from the audience. If you have any, I'd like to invite you now to ask them.
So we have quite a bit of time left if anyone wants to ask anything.
Actually, I have a couple of questions.
Sure.
Does that key, that master key on the KMS side, that is the same, it remains the same for all the time? It chooses different exponent from the client side, right?
Let me pull that up.
Slide, quite in the beginning.
Are you referring to the conventional approach or the new approach?
The new approach,
Okay.
when you were extracting out by the inverse. Yeah, this K.
So the K is the key maintained by the KMS. That's the same each time. However, the B is different each time. So even if you're unwrapping the same key, the server will see a completely random value every time.
Yeah.
Yep.
So did you do any formal kind of analysis to like how secure the value K is with the client side? Because the client send all the time many different W to the power B, and it's always being exponentiated by K, the same K. Does it give away the security of K? Or what kind of analysis you have done in that?
So the result the client gets back is always W to the K, but W to the K will be different for different Ws. And
yes.
Yeah.
K is just an exponent, right?
So the security is equivalent to the discrete logarithm problem, which is the basis of how TLS secures keys today. So if
With discrete logarithm, all the time the exponents are different. And here, in the Diffie-Hellman kind of setup, the ephemeral values, they're different all the time. But here K is the same. Anyway, I was, because the similar kind of concept I was also thinking, I had a paper here in the workshop, so I could take it offline and discuss with you. Like,
I'd be
I'm also
interested
struggling
to
from the security analysis.
review that. I would say because the B is different each time, from the perspective of network security, everything there's zero information exposed.
Yeah, here
about,
B is different, but K is the same all the time. In normal Diffie-Hellman setup, like A and B, both are different.
Right, but the client's, again, the only one that ever sees the same value each time. Over the wire, both what goes out and what comes back will seem different. So, yep, thanks.
Thank you.
Hi, Eric Crockett, AWS.
Hi.
I had a question about the key rotation. So you had said something about a read operation. I was wondering what you meant by that.
Okay. Let's see that. So that was this slide. So what I meant by this is if anyone were to send a read request.
What is a read request? Like an unwrap request?
Just say a get request in the sense of if you consider the storage service as like S3, this would be a get request to the object storage to read an object out of the object storage and return any metadata associated with that. So
I think so. You're assuming that the object is stored in the cloud, sort of like. I mean,
yeah, here the
it
storage
really would require sending every single object to the KMS to update its exponent, right?
in today. So this is assuming that the storage server has some sort of cooperation with the key management system in order to be able to handle deltas. But there's only one time that the storage server interacts with the KMS, and it's when it receives the delta. It will then kind of behind the scenes apply that delta to all of the wraps it has stored. And once it completes that, it can throw the delta away. During that time, however, any read sent to that storage server which hasn't been updated, the storage server will need to perform that update before it returns anything to the client.
Okay, but that's assuming that the client didn't do any external storage with the deck, right? Because otherwise you'd need to store this delta indefinitely to update that value. You know, if I send a value later,
right, yeah.
right?
Right, so the delta, if the client is storing things outside the storage server, this delta could be sent back to the client, and then the client would have to take responsibility for performing those updates.
Okay.
But again, it can be done in an offline manner without having to go to the KMS for each object.
Right.
Yeah, that's a good point.
Okay, and then, so I kind of reached my second question, which is that you don't really store delta in the long term, you just store K prime, and then you can do this key rotation multiple times that way.
Yeah.
Just create a new delta and then do this process over again.
Mm-hmm.
Is that right?
Yeah, you could even have, if 2 rotation requests came in very quickly, you could have kind of a combined delta that could jump you over both rotations. Yeah.
Okay, great, thank you.
Thanks. Okay.
All right, thank the speaker again.
Thank you.